We're ready to get started now on chapter 23. That's all about electric potential and electric potential energy. I expect you're reasonably familiar with this from Physics 1051, but I'll go through a summary on the next slide of the things I expect you know. So here's the list of the things I figure you've already seen and practiced lots in Physics 1051. We'll begin with electric potential energy. We know that electric potential energy, or any potential energy in general, is negative of the work done by the internal forces. If you put in that work is the integral of F dot ds, then it can give us an expression for change in electric potential energy as a function of the electric field, because we know that force is Q times E. So this gives us a way to find our electric potential energy. What we know is that charges released from rest will move to areas of low potential energy. That's familiar if you think about gravitational potential energy. If we have the car on the top of a hill, we give it a little push, it's going to roll down to the bottom. We see the same sort of behavior in electric charges when we see that unlike charges attract each other or like charges repel. So that shows us that there's some potential energy function. There are two special cases of electric potential energy. First is between the plates of a capacitor. So remember, a capacitor is two charged plates, equal and opposite. The potential energy is the charge times the field times your distance from the negative plate. So that gives us the electric potential energy in a constant field or between the plates of a capacitor. I figure you've also covered the electric potential energy between any two point charges, K, Q1, Q2 over R. And if you had a group of charges, you would find the total energy by finding the potential energy between each pair of charges. Okay, so that's pretty much it about potential energy. Next is electric potential. So the idea of electric potential, you can build an analogy with electric field and force. We know that electric field is the force per unit charge. If you put a charge in an electric field, it will feel a force. Just like gravity. If you put a mass in a gravitational field, it feels a gravitational force and it falls down. Electric potential is the electric potential energy divided by the unit charge. So if you put a charge Q in a region that has potential V, it's going to have potential energy U. So that's what potential is. We can use the expression that electric potential is energy per unit charge. We put in that our energy is Q times the electric field over distance to find that our change in electric potential is related to the electric field and its path taken. This gives us a relationship between potential and field. What else? Between the plates of a capacitor, the electric potential is the field times the distance from the negative plate. Near a point charge, our potential will be the potential energy per unit charge, or kQ over R. For a bunch of charges, you find the potential of each one and you add them all up. If the potential is the integral of electric field, then that means the electric field is the derivative of potential. Okay, and we'll do some examples about that. Last, we can analyze the motion of many charges using conservation of energy. So final energy is initial energy plus work done by non-conservative forces. In general, our work done by non-conservative forces means work done by friction and things like that. Typically, that's going to be zero in problems that we study. E stands for mechanical energy. It's kinetic plus potential. In this section, we'll pretty much only think about electric potential energy, but in general, you could have gravitational and spring potential energy as well. And last, we'll also look a little bit at equipotential lines and the relationship to electric field lines. So here's more or less the things I think you've done already. We'll do some review, and of course, you should reach out if you have any questions. This example is a pretty good summary of some of the things we were talking about with conservation of energy. We have an electron with an initial speed of 500,000 meters per second. So let's draw our little electron. It's moving to the right. Remember, electrons are negative. V initial equals 500,000 meters per second. And it's brought to rest by an electric field. So this is where the electron is initially. Finally, it's over here somewhere, and VF equals 0. So let's stop. Before we even talk about these questions, let's think about the nature of this electric field. Our electron is moving to the right and slowing down. If it moves right and it slows down, the electric force must be to the left, because the acceleration has to be to the left. If the electric force is to the left, and we know that electric field is force per unit charge, so force divided by the charge of the electron, so that's our force, divided by minus E. So electric field is force divided by charge. If the force is to the left and the charge is negative, the electric field must be to the right. So I'm going to draw an electric field vector here. So our electron is moving in an electric field that points right, and it feels an electric force that points left. So E points to the right. Okay, so that explains why the electron slows down. Next, does it move into a region of higher or lower potential? There's a little bit to this question, actually. It's a short question, but it's got some thought to it. Let's think about conservation of energy. E final equals E initial plus work done by non-conservative forces. We don't have anything like friction here, so our work done by non-conservative forces is equal to 0. Our E final is our final kinetic plus our final potential equals our initial kinetic plus our initial potential. Let's think about what happens in this problem. So the electron slows. That means the electron's kinetic energy decreases. If the kinetic energy decreases, the potential energy has to increase. So as the electron moves, it goes towards an area of higher potential energy. So electron moves towards higher U. This makes sense when we think about the motion. So if we think about something moving and slowing down, let's go back to our example of gravitational potential energy. If a car is rolling up a hill, it will slow down. As it goes up the hill, it's higher potential energy. So this makes sense, higher potential energy. Now, we weren't asked about potential energy, we were asked about potential. To figure out if the electron moves towards higher or lower potential V, let's remember the relationship between electric potential energy U and electric potential V. So what we know is that electric potential V is the electric potential energy per unit charge. In this problem, the charge is the electron, so it has a charge of minus E. This tells us that V has the opposite sign of U. So if it moves towards higher potential, because V is U divided by a negative charge, it must move towards lower V. Okay, so that tells us about the sign of does it move towards higher or lower potential. So it moves towards lower potential. And we can verify this by thinking about the relationship between electric field and electric potential. We know that delta V is equal to negative the integral of E dot ds. This negative sign right here, this negative sign tells us that electric field always points towards low potential. So on our picture up here, the region where we started would be high potential, because that's where the electric field starts. Over here near the end, where our electric field points towards, that would be lower potential. Okay, so there's part A explained in a couple of different ways. For part B now, what is the potential difference that stopped the electron? So we're trying to find delta V for the next part. To find our potential difference that stopped the electron, let's go back to our expression for potential energy that we wrote down in part A to think about the electric potential energy. So our conservation of potential energy says that final energy is initial energy plus work done by non-conservative forces. We don't have any friction or anything, so that bit is 0. So final kinetic plus final potential equals initial kinetic plus initial potential. So let's springboard off of that and let's fill in what we know for each of our terms. So let's make a list of those over on the side. Well, why don't we just fill them right in the equation? K final is our final kinetic energy. So that's 1/2 times the mass times our final speed squared. I'm going to work in symbols for a bit. If you preferred to put in numbers, you could certainly do that at this point. Our final electric potential energy is the charge times the final potential. Our initial kinetic energy is 1/2 times the mass times the initial speed squared. Our initial electric potential energy is the charge times our V initial. Some of the numbers we're going to be putting in this problem here. Mass of the electron is 9.11 times 10 to the minus 31 kilograms. Our V final is equal to 0. V initial is equal to 500,000 meters per second. What else do we got? Q means the charge of the electron, which is minus the fundamental charge, minus 1.6 times 10 to the minus 19 coulombs. And delta V is what we're trying to find. So since we're trying to find delta V, let's get our V's on one side, everything else on the other side. So Q times VF minus Q times VI equals 1/2 times M times VI squared. Take away 1/2 times M times VF squared. We'll take our Q outside here on the left-hand side. So we've got Q outside of VF minus VI, that's our delta V, equals 1/2 times M times VI squared minus 1/2 times M times VF squared. Keep going on the next slide. So VF minus VI is delta V, that's what we're trying to find, the potential difference. We'll divide both sides by Q. Okay, now we can simplify a little bit. We've got 1/2 times M outside of VI squared minus VF squared divided by Q. Let's pop our numbers in. So we get 1/2 times 9.11 times 10 to the minus 31 kilograms. VI squared is our 500,000 meters per second. That's got to be squared, minus 0 squared, divided by the charge of our electron, minus 1.6 times 10 to the minus 19 coulombs, gives us a potential difference of minus 0.712 volts. For what it's worth, if you weren't sure about how to do A, or if you didn't really understand the conceptual approach of did it move towards high to low potential, you could have jumped right in and done part B first to figure out the potential difference. When we see this, the potential difference is negative, so this tells us it moves towards lower potential.